Hey guys, so today we are learning 1.3. We're talking about infinite limits and limits at infinity. Okay, so infinite limits means that it's going to infinity or negative infinity. Limits at infinity is, hey, we're talking about that end behavior. Okay, so let's review some of the things we um, could remember from last year about rational functions and how to graph them with holes and vertical asymptotes. Okay. So first of all, if we look at this function f of x, we can see that we're going to be able to cross off our x minus 1. Of course, that leaves a 1 at top, okay? Now, because we crossed it off, that means it's a hole. So we have a hole at x equals 1. How did I get 1? Well, I set that x minus 1 equal to 0 and solve. Now, usually in the past, we've been talking about vertical asymptotes, and then we just don't categorize them. But the truth is we have an even or an vertical asymptote, okay? And that comes from whether the exponent is even or odd. So we have an even vertical asymptote. There is our even exponent, but I have to look at the actual binomial and say that we have that even vertical asymptote at x equals 2. The odd, well, look for the odd exponent. So we have a vertical asymptote, an odd one at x equals 4. Now, why is it so important to describe it as even or odd? Well, even asymptotes will go in the same direction from both sides. So it will either go up or down. Where odd ones go in opposite. So if you know the left side, you know the right side. Same thing as if I go down on the left, I go up on the right. Okay, so that's a cute, quick review. So infinite limits. You have seen examples where a limit does not exist at a vertical asymptote. Such non-existent limits can be expressed as infinite limits if the vertical asymptote is either even. So we can say if it's even, we can express it as infinity or negative infinity. Or if we're finding a one-sided limit, because with odd, if you're only finding one side, we can still express that as infinity or negative infinity, okay? We have to be prepared for both, because when we do multiple choice on the test itself, you don't know if that answer is going to be a do not exist offering there, or if it's going to be positive, negative. So we have to get ready for both. So what we're going to do is we'll look at our vertical asymptotes and see where we get our infinity or. Okay, guys, if it looks like I skipped, it's because somebody came in my room and asked for a tissue. You know who you are. Okay, so let me get back to this. The examples below are your odd and even vertical asymptotes. So let's talk about this. First of all, if you look at the denominator here, this is x minus 2 to the first. Okay, so first is an odd asymptote, which means they go in the different directions. Now, since it is odd, that means what we have to do is check the left and right side. Okay, I say that because if we plug in 2, I get 5. If I plug in 2, I get 5. That doesn't help us at all, right? So the idea is, since it's on the right side of 2, I'm going to plug in a higher value of 2, so let's say 3, and that would be a positive asymptote. So we would get, if I plugged in 3, I would get a positive 6 over a positive 1. So that means we are going to a positive infinity, okay? Now here, if I look at this, I'm going to go lower than 2, okay? So let's say 1. 1 plus 3 is still a positive, and 1 minus 2 is a negative. So it is a negative infinity. Okay? Now, Let's see what we have here. We have an even, okay, even vertical asymptote. So that means they're going in the same direction. When they're going in the same direction, guys, I want you to realize that you just need to plug in the 1. And of course, on the bottom, you're going to get 0, which is our asymptote. But on top, that tells us where we go. So if I say 1 minus 2, we get negative 1. We get a negative. Okay, so that means this will be a negative infinity. Okay, so for even, you just have to plug into the numerator. That tells you where you're going. Okay, the other thing I want to mention is if your function is a positive function, your left side goes to negative infinity, your right side goes to infinity. If we are at a negative function, our left side will go to infinity and our right side will go to negative infinity. If you want to think of it that way, think of a negative outside of function makes it flip. Okay? This one, totally different. You need to plug in to that numerator. The great thing is since this is even, and you know 1 is negative infinity, you automatically know the other is negative infinity because they're the same. Just like here, if we did number 1 and we got positive infinity, we automatically know that negative infinity on the other one is odd or different. All right, number 5, well, first, always with limits, right? We plug in. If we plug in, I get 0 over 0. So what does that tell us to do? Think of 1.2. What we do is we write down our limit. X approaches 2. Let's factor the top. We get x minus 2 times x plus 2 all over x minus 2. What do you know? This crosses off, so that means we have a whole at 2. And so now when we plug in, we actually have our limit of x approaches 2 to x plus 2, which when we plug in now, we get 4. Okay, very good. All right, so that's our vertical asymptotes, even and odd. Now let's talk about limits at infinity. If a graphing function of f of x approaches a horizontal asymptote to the left or to the right, f of x is said to have a limit at infinity. If the asymptote is y equals L, then the limit as x approaches infinity equals L. In other words, limit at infinity gives us the end behaviors. So remember, we talked about end behaviors. Where is it going to? So for large values of x, the highest degree term in the numerator and denominator. So if we look at the highest degree in the numerator and the denominator, that helps us determine where our horizontal asymptote is. So let's do some review. Horizontal asymptotes are things that we've done in secondary 2 and 3, mostly secondary 3, okay? So one of the things that we realize with horizontal asymptotes, again, we look at the highest degree in the numerator and the highest degree in the denominator. When your exponents are the same, you have a horizontal asymptote at the leading coefficients. So in this case, we have a horizontal asymptote at y equals 1/2, because 5 over 10 is 1/2. So when we have the same, it's the coefficients out front. Now on 7, if we look at our highest degree, we have x to the 4th on top and x to the 5th on the bottom. When the highest degree is lower on top than it is on the bottom, you have a horizontal asymptote of y equals 0, automatically 0. For 8, as you can see, the degree on top is higher than the degree on the bottom. This means there is no horizontal asymptotes. Okay? No horizontal asymptotes. So how does that help us with limits? Well, it actually gives us our limits. So for number 9, as you can see, it's the same thing as number 6. So again, it's the same highest exponent. So we just take our coefficients up front, which is 1/2, and we're done. On number 10 here, as you can see, our numerator is smaller than our denominator exponent. So right away, 0. Now, I want to show you guys something. So when you think of these graphs, right, and let's say have the horizontal asymptote at 1/2 for number 9, don't forget this is end behavior. It doesn't matter what happens in the middle, it's about the end. So no matter what, as we go to negative infinity, it's getting very, very close. And as it goes to infinity, it's getting very, very close to that y equals 1/2. So that also goes for the y equals 0. Sorry guys, somebody else came in. All right, so same thing. If the horizontal asymptote is 0, it means the end behavior. As we go to negative infinity or as we go to infinity, it's at 0. Now, 11, what happens when there's no horizontal asymptote? Okay, well, what we still do is we look at our highest degree, and then what we're thinking of is breaking it down, okay? So if we broke this down, x to the 4th over x cubed would be x to the 1st. And x to the 1st graph is a linear equation, and it's a positive out front, so that's why it goes from down to up as you go left to right. And since it's infinity, well, as we go, let me do a different color. As we go to the right to infinity, where is our graph going? It is going up. So our answer is either infinity or does not exist. Okay, either one's fine. All right, number 12. So same idea, we got to check for those horizontal asymptotes, but the problem is we're in factored form. And the last thing you want to do is multiply, multiply, multiply. So all we care about, remember, is the highest degree. So we've got a 2x and we have an x squared. So 2 times 1 squared is 2. X times x squared is x cubed. And then, of course, that would just continue, right? We don't care about everything else, though. We just care about that first term. Here, we have x times 3x squared. So be careful that, because it's 1 times 3 squared. 3 squared is 9. 9 times 1 is 9. Then I have x times x squared, which is x cubed. Dot, dot, dot. Okay. Your biggest mistake will be to forgetting to square that first term. Okay, so watch out. Now, if you see the exponents are the same, and when they are the same, we take the coefficients. So that means 2 over 9 is our limit. Okay. All right, one more step, guys. Well, 2 more actually. So rational functions like the ones above at most have one horizontal asymptote. So the limit is the same whether it's approaching negative infinity or infinity, right? So like I said, this little graph here, they're both approaching the same horizontal asymptote. But radical functions have 2. Okay, this is where we have to be careful. So remember how with horizontal asymptotes, we always look at the highest degree. So if I were to look at this highest degree here, we have an issue. The square root of 4x squared. Well, what is the square root of 4x squared? That would be 2x. Okay. Now, before I go forward, I want to remember, because I'm not just plugging in yet, I do have to rewrite this limit, and I want you guys to get used to that. So limit as x approaches infinity. So again, the square root of 4x squared is 2x. Now, here's the problem with that. We have both sides of it. There is a positive and a negative. But the truth is, what is the only value that we can get out of a square root? The only value that exists out of a square root is a positive number. So that means we need to have the absolute value around it. Again, the absolute value must be around it because when we take a square root, we can only come out with a positive number in this case. Okay, and then of course that is over x. Now, if you look, guys, these are the same. This is x to the first, and this is x to the first. So when they are the same, we look at the coefficients in front. So the coefficient in front is 2 over 1. Now, another thing that I want to keep in mind is I'm going to a positive infinity. Well, the absolute value of a positive infinity is a positive, and the absolute, or not absolute, positive infinity in the denominator is also a positive. So our answer is 2. Now, what happens when it's negative? Okay, because as you can see in 14, it's negative there. So again, I'm looking at limit as x approaches negative infinity of absolute value of 2x all over x. Okay. Same idea, it's to the first, right? So I take the coefficients in front. So I get 2 over 1 for the coefficients in front. The problem is right now is if I were to plug in negative infinity. If I plugged in negative infinity in the absolute value, I get a positive. But if I plug in the negative infinity to the denominator, I would get a negative number. So I have a positive over negative, which is a negative. So going to negative infinity, I am at negative 2. Okay, so be careful with that. All right, now we're looking at ease. Okay, sometimes with the easiest way to do that, especially with just the function e, is I want you to look at the graph. Okay, so let's look at the graph. E, of course, goes through 0, 1. We have a horizontal asymptote at 0, and our right side goes to infinity. So right away, we can answer these questions. The limit as x approaches negative infinity to e to the x is 0. We know this just from the graph. This is a fact. Limit as x approaches infinity of e to the x, well, that goes to infinity, but we also know that we can write does not exist. We have to be ready for both types of answers. All right, I'm going to rearrange number 17 because of this negative x. Okay, so I'm going to write limit as x approaches infinity, and this is going to be 1 over e to the x because negative exponent puts it back in the denominator of 2x squared minus x all over x squared plus 3. We're going to take each of these separately. So we're going to do the limit of this one and then the limit of that one. Okay, if I plug infinity here, I get infinity, right? We already explained that when you plug in infinity to the exponent, it goes to infinity. But what happens is I don't want to think of it as infinity, guys. I want to think of it as a large value. So really, what's happening here is as the denominator is getting larger and larger and larger, it's actually going to 0. This is going to be a nice fact to remember, okay? So this first part, we have 0, 1 over e to the x. As x approaches infinity, goes to 0. And then the second part, if you look, we have the same exponent. Remember, the same exponent makes you take the coefficients in front. So the second part goes to 2. So now we know that the limit of this function as x approaches infinity is the value of 2. So I had to take those separately. Okay. All right. What does that mean for 18? Okay. So we've always been told before to look at the highest exponent degree, excuse me, when you look at the numerator and denominator. So in the numerator, our highest degree is 2x or x squared, so 2x squared. Our highest degree, well, think of this. This is 2 and this is x. This x can go up to infinity. So the highest degree is the term e to the x. So this is what I'm going to focus on, okay, guys? So right now, I am just going to rewrite this so I focus on that x approaches infinity of 2x squared over e to the x. Now, if I plugged in, okay, if I plug in infinity here, infinity squared times 2, right? So it's a large number. If I plug in e to the infinity, I would get infinity. I would get a large number. Now, here's what I want to point out. This denominator right here is growing faster. Okay, think of it. An x squared is like this, your parabola, right? But your e to the x is growing faster. It's coming up faster than our parabola. So since the denominator is growing faster than the numerator, that means our limit is approaching 0. Just like if the denominator has a higher exponent, you have a horizontal asymptote at 0. So think of this as the higher exponent. So our numerator is smaller, denominator is bigger, automatically making a horizontal asymptote at 0, which means the limit is at 0. Okay, guys, one thing I want to keep you in mind, right? When we're going to infinity and in negative infinity, that is your end behavior. That doesn't conclude what happens inside. Okay, example, I just want to show you another graph just in case. If I have all of this inside and then all of a sudden it comes down and it goes back up here and it goes this way, that end behavior is going to 0. Okay, the end behavior has a horizontal asymptote at 0, but what happens in between, we can still have it go through the x-axis. That will make more sense as we go along. All right, thank you for your time, guys. Sorry about the interruptions.